Presenting what?
Presenting to be ChatGPT.
Oh, okay.
It's only about a minute long. You can check it. That's right, yes. Also, Illustrated got accused of using ChatGPT.
Mike is on a beach in Abu Dhabi right now. I begged him to take me along. Okay, people, it is 11:10. Our oh, I need that mic.
Shall I wheel you over there?
Huh?
I'll wheel you close to that.
Close to what? No, I have this.
Ah, okay. All right.
Some buttons. Got it.
There you go.
Well, welcome to the Climb Seminar. Today we have the privilege of a lecture from my very good friend B.R. Kumar. Kumar is some named distinguished professor at TAMU, don't know the name, the Greg Abbott Chair at TAMU. I met Kumar when we were both on the faculty at Illinois. Wonderful years, and he's so knowledgeable. And as I was telling Jean, when we'd go on a flight, he would school me on, you have to know this, you have to know this. And he never criticized me for knowing so little. And he's won every award. He's won the Control Systems Field Medal, the honorary doctorate from ETH Zurich, and I think those are the two big ones. The Ekman Award, it's a minor award because I won it, so it doesn't count. And he's, above all, besides being so smart, he's a wonderful human being. So, Kumar, over to you.
Thank you. Thank you. I have a mic here. Thank you. Yeah, I think being introduced by Kameshwar should be one of the high points of anybody's life. Anyway, so I should tell you that this is actually a unique experience for me, because usually my trip to Berkeley means coming here, going to Corey, and then going for lots of walks with Praveen, and then going back. That was it. So this is the first time I'm not walking with Praveen, and I'm giving a seminar too. Okay. All right, so I'm going to talk to you about exploration versus exploitation, from adaptive control to reinforcement learning. And this is an area that many of us in control have been fooling around with, and some of us have started re-fooling with it in recent years. So I'll just tell you some of my thoughts. Okay. So this thing started actually with my student Art Becker. Actually, these two were my first PhD students 45 years ago. Okay. And Art Becker came up with a brilliant idea, which I'll explain during the seminar. And he's currently at National Security, NSA, completely uncontactable. Okay. And, or at least I haven't been able to contact him. And then Waylon also was another student, and many other people have been part of this voyage. Okay, I'm going to start with some stuff which all of you know about. Okay, but just to set the tone, and then we'll get into some new stuff a little bit later. Okay, all of you know about the bandit problem, and let's say you have Bernoulli bandits with probability of success theta 1, theta 2, and every day you're forced to play an arm. You want to play the larger one, but you don't know which is larger. What should you do? Of course, you should explore a little bit, and then at some point you want to exploit. So how to do this? Exploration can be valuable, but it's costly, and what's the best trade-off? Okay, so that's the bandit problem. And you have a fundamental trade-off here between exploration and exploitation. Same thing in control also. The holy grail of control, right, from 1950 onwards was adaptive control. And the idea was you're given a black box, and then you want to connect this adaptive controller to it. And very early on, it was recognized that this control would have two purposes. One is, by choosing the control, you can excite the modes of the system and learn about them. And the other was actually to steer the system to some position. Okay? So excitation and control, and in fact Feldbaum in the then Soviet Union coined the phrase dual control. Okay. And by the way, people started implementing adaptive control, but not with any theory. Okay, so there was in fact a famous plane crash X-15, which was supposed to have an adaptive flight control system.
Kumar,
Yeah.
you might want to watch the edge.
Yeah. Okay.
Don't go back.
All right. So, yeah, which crashed in 1967. But the reasons for it crashing were very complicated. The adaptive control law is last on this list: electric power, flight control, instrumentation failures, etc. Okay. But anyway, what it did was that sensitized the field to developing adaptive control rigorously from a stability viewpoint. Very much. It re-energized this whole Lyapunov approach to stability in adaptive control. And the overall system, even though the nominal system may be linear, the overall system is non-linear, and trying to prove the stability of this kept the control field busy for 25 years. Okay. All right. Okay. Several contexts have been studied. Multi-arm bandits, self-tuning regulators. I'm going to say something about these two things, and then Markovian systems. Okay. So let me start with an early history of banditry, which most of you probably know, but just for completeness. So apparently the first mention is due to Thompson in 1933, and he actually raised the context of drug testing. Okay, he said, if you have two drugs, which will you give? And he was a pathologist at Yale University, and this is the title of his paper on the likelihood that one unknown probability exceeds another in view of the evidence of two samples. And his rationale for the Thompson sampling he came up is basically in this equation, which I'll try to decipher in a second. But what he did say is it seems apparent that a considerable saving of individuals otherwise sacrificed to the inferior drug might be affected. And this was a nice line for the talk in the last 4 years. Okay. And also the use of data as a guide to action. Okay, and how to get more of the data. Okay. So Thompson's randomized sampling, this is the kind of the way he justified it, or as best as I can figure out. He said, suppose, he adopted a Bayesian viewpoint. He said, supposing P is the probability that arm 1 is better, and now supposing I play arm 1 with a monotonically increasing probability f of P. Okay? Then, if arm 2 is better, with probability 1 minus P, it's actually arm 2 that's better, but you play arm 1. Whereas conversely, with probability P, arm 1 is better, but you play the reverse. And he said these two things will be equal if Fp equals P. Okay, more or less that's what I can make out. And that's Thompson's randomized choice. He says play an arm I with the probability that is in fact the better arm. And now this is called Thompson sampling, and still one of the best policies in the field. And Thompson, very interestingly, even constructed a machine. So he said, let's suppose we take a beta distribution. Okay, so I have two independent beta distributions for the two arms. This is the conjugate priors. So beta with S1 successes, F1 failures, another one with S2 successes, F2 failures. Then you want to play an arm with arm 1 with the probability that this exceeds this. And he showed that this is equivalent to a certain configuration of blue and red balls. So if you put N1 plus 1, N2 plus 1 red balls, blue balls, then what's the probability that you'll find S1 red balls before S2 blue balls is equal to this probability, and he built a machine. And they actually tested out this algorithm using this machine, cardboard box, etc., and said how beautifully it worked. Okay. And by the way, this thing was published in a mathematics journal. I found that very interesting. Okay. The frequentist viewpoint was advocated by Robbins, who apparently didn't know anything about Thompson's work. Doesn't cite it. Okay. And he considered just the approach where these are just unknown quantities in the interval 0 to 1, and you're interested in getting the long-term average probability equal to the maximum of that, long-term average reward. And he said this represents the simplest, in a simplified way, the general question of how we should learn from past experience. And he also had a beef. Most statisticians have a beef. They say that the statistician is consulted, if at all, only after the experiment is over. Just like control people, right? They say, you come and ask us to design the control law after building all the hardware. Same thing here. And that was one of his beefs. And he also came up with a scheme to solve this long-term average problem. He said, these are kind of a forced choice schemes. So let us suppose you have the times 1, 10, 100, 1,000, 10,000. And you alternated those times between the red and the blue arms. So time 1 you play red, time 2, 10 you play blue, then 100 you play red, etc. And the rest of the time you play whichever is empirically better, then of course it converges to the max. Okay. A Bayesian formulation, fully Bayesian, was adopted by Bellman in 1956, who was just popularizing his dynamic programming method. And he said this is a general problem in the general field of learning processes where we must determine the structure of a process while carrying on an experiment. And he wrote down this dynamic programming equation, which is this is the beta probability of success. And if you get a success, the number of successes updates. So you can write down this dynamic programming equation. And he was quite surprised that it is so difficult. And for a long time, this was considered intractable. And then Gittins and Jones in England in 1972, they showed that every arm has an index. This index is the maximum over stopping times of discounted reward divided by discounted time, and you should play the arm with the largest index. And there's a beautiful proof of this that Jean Valrand also has come up with an interchange, nice interchange argument. Okay, let me turn to self-tuning regulators. So the self-tuning regulator of Ostrom and Wittenmark. Now, in the process control field, a very widely adopted model is RMAC systems. So these are systems, in the Swedish notation, Q inverse is the backward shift operator. So you have a Y, depending on U, the input, and this is, say, white noise. So for example, this is, why is this not moving? Okay. So this is an example of an RMAC system. Okay. And basically this thing, these terms model colored noise. Okay, if you will. And let us say the goal is to minimize the variance of the output. And this is actually a popular objective in process control. And in fact, the first application of this was to paper thickness control in a paper machine, because paper sold by minimum thickness. So typically you'd set it at mean plus 3 standard deviation. So if I can reduce the standard deviation, then I can economize a lot. And so, yeah, and in many process control applications, actually minimum variance control is a reasonable thing for a good product. Okay. Now, the issue is the analysis of this actually took many decades. Okay. So you have your, let me first do it for the ARX system. So let us suppose there's just a white noise term there. And this is your minimum variance controller. Basically, it tries to make sure that this and this is all cancelled out, and you simply get y equal to w, right? Now you can model that as a linear model with some regressive vector times some parameters. This is the parameters, and that's your regression vector. And you can either do a least square or a stochastic gradient algorithm to fit the minimize the sum of squares and do a certainty equivalence. That is, once you have an estimate, then you use that estimate in the same way that you would use the real parameters. And the thing is that you get a nonlinear stochastic system. Okay, and this was a very complicated thing for the field. It took many decades to finally say something about the stability of this convergence and things like that. Okay, first breakthrough of this was by Goodwin, Ramage, and Keynes in 1981. Okay. Okay. Now there were some very interesting things that happened here. This was not completely a model-based system, like model-based approach, like we think of it, because the distinction that time was not model-based and model-free, but direct and indirect adaptive control. So indirect means you estimate the model, then you do the controller. Direct means you adapt the controller weights. And let me show you how that arises. So now let us suppose that you have this colored noise. Okay, so this is a much more general model of a linear system. And because these things are not known, these are not observed, it's actually a partially observed system. Okay. But it turns out that the same algorithm as I had earlier, exactly the same, which assumed that the noise was white, also works for the colored noise case. And the reason is under optimal control, the residuals are in fact white. Okay, so it's a kind of a bootstrapping method. Okay, and but if you really want to identify the system, then you have to do more complicated things. And this actually, still some of these problems are unsolved. So supposing you really want to identify the model, and if you write a regression vector this way, the regression vector components itself you don't see, okay? But you can kind of bootstrap them. So you can approximate these noises by residuals of your estimate, and then do a bootstrap, and you can actually show that under some positive real conditions, etc., that this thing converges. Okay, so there's a lot of work done in this area, and the general problem without this assumption is still very much an open problem. Okay, so there's still a lot of open questions around here. Okay. Okay, so generally this whole approach to self-tuning regulators and so on, one set of questions is stability. This thing shouldn't blow up. It should be self-optimizing. And that was answered by Goodwin, Ramage, and Keynes in 1981. The second issue was, do the parameters of the controller actually converge? Do they self-tune? And that was answered by us a few years later. And the least squares approach, as opposed to a stochastic gradient approach, is much more difficult because asymptotically the least regression matrix becomes ill-conditioned. As you converge, you lose rank, and that becomes a huge problem. And that was answered by Goodwin and Goguo and Chen. Okay, robustness also, we took, so what may be interesting is the approaches we took in those days compared to, say, what we're doing now. So robustness, this problem became a red-hot problem. It was phrased as, what if there are unmodeled dynamics? No matter how you model a dynamic system, there are always some high-frequency dynamics that are not modeled. Okay, and or to put it in the statistician's language, the true model is not in the parameter set. And this was a model that actually took the field by fire. So a bunch of people at MIT, Mike Athens, Lena Valavani, Rose Stein, etc. They took a system nominally with this first order system, but added a pole very, very far away. Okay, and it turned out that that thing actually causes instability. So this took the field by storm, and many solutions were investigated to try to fix it, and this took another 10 years. Okay, etc. All right. Ultimately, I'll show you one of our theorems, kind of an esoteric theorem to address robustness. So we can actually show that an adaptive controller has many of the has these properties. It attains optimal regulation and tracking in the ideal case where all the assumptions are satisfied. Okay, and it's however still mean square stable. Even if the noise doesn't satisfy the positive real condition, and it is still mean square stable. Oh, it's mean square stable in a graph topological neighborhood of an ideal plan. This is a topology under which stability is kind of continuous, and it continues to stabilize the system, and the adaptation gain is prevented from vanishing. So a lot of under a lot of properties, it was stable or optimal or whatever. Okay, so that's the kind of result we proved. Okay, now let me move to Markov decision process, and hopefully we'll come to the present era soon. So here's the adaptive control problem for Markov decision processes. So you have a state space. Let's assume for simplicity everything is finite. Okay, the tabular case. So let's say a bunch of finite states, bunch of actions, and when you take an action U, it goes from I to J with a certain probability. Unfortunately, this probability depends on a parameter theta, which is not known. So it's unknown, but you know that it belongs to a set capital theta. So this is like a frequentist or a non-Bayesian approach. And then you incur, and then you get a reward also. In the old days, we used to talk of costs. Now it's rewards. Okay. All right, reward. And now the approach that we investigated, actually the first investigation of this was by Peter Mandl in the Charles University in the then Czechoslovakia. Okay, so this is a problem he looked at. He said, for each parameter theta, determine an optimal stationary policy for this long-term average reward problem. And now there is a true parameter, but you don't know what it is. And your goal is to maximize this, etc. And we will apply certainty equivalence. So we'll make an estimate, and we'll use that estimate instead of the truth. Okay. So that was Mandel's approach. So estimate it, and the natural estimate in this context is a maximum likelihood estimate. You have this is the probability of a trajectory under theta. Choose the theta which maximizes this. That's a maximum likelihood estimate, and then assume that's correct, and then use that estimate in your control law. Okay. Many questions. Does it self-tune? Will it converge to the true parameter? And Mandel gave a certain identifiability conditions under which it is true, but these are extreme. Basically, no matter what happens, you're always learning. That's what this condition says. It says, no matter what state you're in, what action you take, you can distinguish between two parameters in terms of their outgoing probabilities. So you get information all the time, so you're always learning, but this is not true even in, say, the bandit problem. Okay. Okay, now we are approaching another seminal work at Berkeley. So this is Vivek Borkar, his PhD thesis. And he said in general, things are going to go wrong. The answer is no. And there's actually a fundamental closed loop identifiability problem. So this is the days before the words exploration, exploitation were coined. Okay, so after dual control had been coined, but this is another phrasing of it. It's closed loop identifiability problem. Okay. So suppose theta hat, your parameter estimates converge to some theta star, and you can prove this under some priority orderings and stuff like that. And let's assume the control laws also converge. Okay, the corresponding control laws converge. Okay, then this is the actual system that's running out there. The true system is being governed by a true parameter theta 0, and is being controlled by a control law which is correct for theta star. So this is the actual closed loop system. But what you think it is this. You think you have your estimate theta star, so you think this is the dynamics, and you know that this is the control law, so you believe this is the closed loop. Now if you have any halfway decent estimator, they have to be the same. Otherwise, you would revise your estimate. Okay? So, your parameter estimates will converge to a theta star, so that under the control law corresponding to that theta star, theta 0 and theta star are indistinguishable. Okay? So that was Vivek's result. But however, this control law is not optimal for theta 0, so you can get stuck in the wrong thing. Basically, the problem is as theta hat t starts converging, you stop exploring and learning about the system, and after some time you're only learning under theta star and you're stuck there. Okay, so what's the solution to this? So this was my first two PhD students. So we looked at this, Vivek had just graduated, so those were the days. And we looked at Vivek's thesis and said, okay, how can we fix this? Okay, so we came up with this method, which may be of interest to you. Actually, most people in machine learning still don't know this method. Okay, but here it is. So, I'm sorry? I beg pardon?
He said there's lots we don't know, and I said there's not a lot we know.
So this is so we discovered that there's a bias of maximum likelihood estimate. I'll explain what that is. Okay. So let V optimal theta be the optimal reward attainable if the model was theta. So how much juice can you squeeze out of the model theta? What's the maximum reward? That's V optimal theta. Okay. Now the fact that these two systems are equivalent in closed loop, right? That the true system with this feedback and the imagined system with this feedback, the fact that they are equivalent means that both these systems will generate exactly the same rewards. Exactly. Okay? But this configuration is optimal for theta star, because for theta star this is the optimal policy. So this reward that you get from this configuration is the optimal reward for theta star. However, this is suboptimal. This control law is not optimal for theta 0 in general. Therefore, the reward you get is less than what you could possibly get for theta 0. Therefore, you will converge to parameters which have an optimal reward which is less than the optimal reward attainable for the true system. So this is a one-sided bias. Okay? But actually you can, so parameters converge to a smaller optimal reward. But you can even write this inequality, which is actually interesting. Okay? So look at the optimal reward attainable from theta star. That's the reward that you would get if you apply the optimal policy for theta star to theta star. But this and this behave the same way because of closed loop identifiability. So the reward that you get for this policy, for this parameter is equal to this, but this is optimal, suboptimal. Now, supposing you could somehow make this less than or equal to this. Supposing you could close this chain, then you'll have equality throughout, and then this phi optimal theta star will be optimal for theta 0. Okay, so that was the idea. So, can we bias the estimate delicately to favor parameters with higher V opt to get the reverse inequality? So then I self-tune to the optimum. Okay. By the way, this does not imply exploring all possible things. It's exploring in a very one-sided way only. Okay, so it's kind of economical. Okay, so this is what this is the solution we came up with. We said we're going to bias the maximum likelihood estimate to favor parameters with larger rewards. How so? So this is your maximum likelihood estimate, right? You choose a theta which maximizes the likelihood. I'm going to introduce here a term which favors parameters theta with larger V opt. But I'm going to do delicately, I'm going to raise it to a power alpha t, and this alpha t is going to go to infinity, it's going to diverge, but slowly, little of t. Okay, for example, square root of t or log t or whatever. Okay. And in fact, a delicate balancing act is needed because this needs to be small enough that it doesn't damage the maximum likelihood estimator. You can't just fool around with the maximum likelihood estimator, so this should be small enough. Yet it should be large enough that it actually moves it to a parameter estimate which is larger reward. Okay? And I'll just sketch out roughly the idea. The proofs are much more complicated, but let me show you why this bias that I'm talking of going to infinity but little of t is. First, let me show you why it is small enough. Okay? You can think of it this way. So I want to show you that if you do alpha t equal to little of t, that's the bias will be small enough that it doesn't damage the maximum likelihood estimate. And so just take the log of this. So instead of maximizing this criterion, maximize its log, and then this product becomes a summation. Now this term grows like little of t because there's an alpha t, whereas this term, if there's any, it grows like t basically. Okay. So it's not big enough, okay? It doesn't damage the closed loop identification. Is it large enough? To see that it's large enough, instead of looking at this criterion, look at the normalized version where you divide it by a constant, not depending on theta, in particular the same criterion for the true parameter. So this is a likelihood ratio, okay? Maximize that. Now, suppose V optimal theta is less than V optimal theta 0. That is, you look at parameters with a smaller optimal reward. Then since alpha t goes to infinity, this goes to 0. However, this is a positive martingale for each theta. It's bounded, and therefore the 0 will kill this whole thing and make it 0. However, for theta to be a maximizer, it should be at least as good as theta 0, and theta 0 will make this 1. So maximizer will keep this ratio larger than 1, whereas if this was smaller, it will go to 0. So preventing such becoming limit points. This is easy to see in the finite case. In the more general case, it's more difficult. Okay. So hence, so we have to prove, actually for difficult context, we have to prove this on a case-by-case basis, and that does become painful. Okay. Okay, so basically it will converge to this, and phi optimal theta star is optimal for theta 0. Okay. So this is the kind of theorem that you get. Use this reward bias maximum likelihood estimate, where you bias the estimates in favor of parameters with larger rewards, attainable rewards, and then use some certainty equivalence control. So pretend that is correct and choose the correct control law. Then you will get long-term average optimality. Okay. Even at that time, we recognize that for bandits, you actually get an explicit index. Okay. So let's go back to this two-arm bandit problem. Okay. Then your parameter vector is theta 1, theta 2, and V theta is just maximum of theta 1 and theta 2. So you can write down this criterion, this bias likelihood criterion, write down the explicit solution. And if you have SI successes and FI failures and NI pulls, then this reward bias maximum likelihood criterion becomes simply this. If you look at it, this is the likelihood function. S1 successes on something with theta 1, S2 with theta 2, and then this maximum raised to alpha. And you get an explicit index. Very simple index formula, which is this. Okay, you choose your alpha, which grows slowly to infinity, and just maximize this and you're done. Okay. And in fact, this was explored a lot by many people in the field. For example, we looked at LQG systems, nonlinear systems, and Tyrone Duncan and Vivek Borkar looked at this for controlled diffusions, etc. So they generalized this approach to get long-term average reward optimality for a whole bunch of systems. Okay. Now, one reason I want to say the self-tuning regulator, we did not worry about identifiability there because it has no inherent identifiability problem. So just to see this, supposing you have these two systems, one with A0, B0, one with A star, B star, right? And your goal is minimum variance control. Then the optimal control law for this system is to cancel these two, right? You get y equal to w. But then y is equal to w, and the closed loop system behaves this way, which means it's optimal for this also. Okay? So it's also optimal for theta 0. Okay, so all I've been talking about so far are long-term average reward. Then a few years after we had done this, actually Hsieh and Robbins came up, started looking at regret. Okay, so they introduced this finer measure. They said, let's not just look at the average of this over time, but let's look at the actual departure of the total reward from the maximum average that you could get. Okay, so that is the expected regret. And everything that I've been talking about basically simply says regret is little O of t. But Hsieh raised this question, how small can we make this regret? Okay, and then came up with a beautiful answer and a solution. So the answer was this optimal regret divided by log t converges to a precise constant which depends on the Kullback-Leibler divergence, etc. But identified basically this constant and the precise asymptotic. And they also came up with an optimal policy which is actually kind of totally well known in the field of reinforcement learning. So this is the policy with the optimal asymptote. They said, hey, listen, write down a confidence interval for each arm. So this confidence interval will have a lower end point and a higher end point. It's a high confidence interval. And play the arm with the highest, with the largest high end of the confidence interval. And the rationale is this, the confidence interval's upper bound will be large, either if the mean is large or if it has not been explored enough. If it's not explored enough, then there's a huge uncertainty, so the high will be large. And that actually turns out to be an optimal trade-off between exploration and exploitation, and this is called the upper confidence bound policy and universally known in reinforcement learning. Okay. And so that raises the following question, which we will get into in a second. So everybody in the field knows optimism in the face of uncertainty. That's what Hsieh and Robbins says. But both these policies, RBMLE and UCB, embody this optimism in the face of uncertainty. the reverse biased approach directly biases the arms towards those with larger theta, whereas UCB prefers arms for which there's a chance of a larger theta. But both are optimism, and it's a wonderful philosophy, right? When you're uncertain, be optimistic. So what's the connection between them? What's the theoretical regret guarantee of this thing? Because I only looked at the average reward case. In fact, I stopped looking at this for 30 years or so, until one of my students said, hey, let's go back to machine learning. How does it perform empirically, etc., etc. And that's what I will talk to you about now. So back to finally to the 21st century. Okay, let's go back to multi-arm bandits. Okay, we'll consider an exponential family of bandits. Okay, it's a single parameter exponential family. Okay, so we'll look at arms for which the reward distribution satisfies this, and the mean value is the derivative of this. So all of this follows from standard properties of exponential family. And the reward bias maximum likelihood method, this would be the likelihood ratio, but then you have a biasing in favor of parameters with larger rewards. The mean reward is the derivative of this parameter, etc. And you can actually explicitly maximize this. You can choose any monotone function here. So in fact, if you choose it to be the log to cancel the exponential, you can do a lot of algebra, etc. And you can come up with this explicit, well, in general, you can come up with this solution. And play the arm with the largest index. And I will tell you the explicit indices for some policies. So this makes it interesting that you can get very simple formulas for different distributions. So as I told you, for Bernoulli bandits, this is your explicit index. Okay. For exponential, it's interesting. So basically, a bandit gives you an exponentially distributed reward. Okay. Look at for each arm, look at the total reward you got from it, divided by in the denominator you have the slowly growing function. Okay. So that's it. That's the index, and that will give you optimality. In the Gaussian case, you add alpha t to the reward you get and divide it by the total time you played. Okay. So simple indices. Okay. And we can show what's the regret performance, because we have not proved regret results, so we went back to the drawing board. Let's look at regret. So one result is if you choose alpha t to be gamma t log t, where gamma t goes to infinity, then the regret is of order gamma t log t, but we should do better. Suppose the lower bound on the gap delta is known, then you can get a log t, but you want to do that without knowing it, and in fact you can adapt this delta hat t and come up with a bound and come up with a log t regret. Okay, I want to talk to you about empirical performance, and it seems like this is pretty good. Okay, so let me show you. So the current empirically good policies for minimizing regret in the bandit case, Thompson sampling is still one of the best. Still, okay, it's amazing. UCB, now UCB has been very streamlined by the machine learning people. So ultimately, the confidence interval has just been reduced to this very simple formula. Okay, and another good one is this information directed sampling. It's kind of a heuristic of Ben Van Roy at Stanford. And he said, we want to balance between exploration, which is maximize information about the optimal choice, and exploration. And he suggested, let's put one of them in the numerator, another one in the denominator. Okay. So now but to minimize this, it requires high dimensional integrals and computations and so on. So it's computationally very, very, very expensive. Okay, but these are among especially Thompson sampling. It turns out UCB doesn't perform very well in the non-asymptotic regime, because this asymptote kicks in very, very huge numbers. Very huge. In the transient thing, it's really not a contender at all, okay, as we'll see. Okay, so here's some empirical testing. So this is the Bernoulli bandit we did with 10 arms, with these arms differing slightly in probabilities, okay. And this is the empirical regret, okay. And our policy actually does pretty good regret. If you look at UCB, for example, it is this. UCB is. So there are a whole bunch of policies which are good. In fact, this IDSS is a pretty good policy. I don't know where it is. Yeah, this one. It's pretty good. Okay. Now, what I want to also show you is computational complexity here. Okay. So I'm plotting. I'm going to plot. Because, see, our policy is actually a very good computational complexity because there's an index. Okay, so not much is needed. And what I'm plotting here is the regret on the x-axis and the computation time per decision on the y-axis. And ideally, you want something here: small regret, small computation time, and ours is around here. IDSS is pretty good on the regret, but requires orders of magnitude more computation. And you can look at all kinds of other metrics if you like. Same thing with Gaussian bandits. Again, policy is pretty good, okay, and it has pretty good computation time and regret. Actually, the computation time would be even down here, except that we are doing this adaptation. So because adaptation, it takes effort. And the exponential bandits also, same story, okay. This is the thing. All right. Now, how close are these policies to optimal? This is just on the side, it's just not very useful, but we're trying to obtain lower bounds, etc. So we can actually prove lower bound. If you want to prove non-zero lower bounds, it's not completely trivial, but we can. Okay, and this is the kind of lower bounds as opposed to what. So this is a lower bound, and these are the policies. Okay. Same kind of results go through general. This approach can be applied in general. So contextual bandits. So if you have these contexts generated by an adversary, and the reward is linear in the context, noisy, and this is the RBMLE policy. We throw in a little bit of regularization here, and then you can get that kind of regret. And performance is still pretty good. Okay, so this thing is over here. It's actually still one of the best. Okay. Markov decision processes also, if the gap is known, then with an epoch-based algorithm, you can get O log t, and again, regret is pretty good. This is Thompson sampling, which is pretty good. Okay. And this is another UCRL2. This is an embodiment of the UCB upper conference approach. And we generated random MDPs with 20 states, 50 states, etc., and it seems to be okay. We tried this for linear quadratic sub-Gaussian systems. So suppose the noise is sub-Gaussian, standard assumptions, quadratic costs, etc. And we have, this is the biasing that we're using in this method. This is the quadratic. Now here we are not able to prove the results without also including a constraint to the upper confidence set. Okay, so we needed to further restrict the maximization of this to the upper confidence set in order to prove results. But it turns out that in all cases this constraint was slack. Okay, so it's not needed, but we cannot prove it without it. Okay, and I'll have some comments to say about this in a second. Okay, and this is the upper confidence set. Okay, it says your quadratic deviation is less than something. Performance is again pretty good theoretically, and okay. Oops. Okay, there's too many things to see here, but these are all examples from other papers. There was a purported model of a Boeing 747, a UAV, an unstable Laplacian, something with large transient dynamics, and in all cases, our policy, this augmented reverse bias method does pretty good. Okay, there are some other policies which do pretty well actually. Okay, for example, this what they call input perturbation. This is what in the old days we used to call control policies with excitation thrown in. So you add excitation to the control law. Kamesh knows all about that. He's written many papers. So that turns out to be pretty good. Okay. All right. So let me now say something about this whole business of optimism. Okay. Some insights. So both, as I said, both these things embody the principle of optimism in the face of uncertainty. Okay. And the biased method directly reward, it biases in favor of arms with larger rewards. And then the Lie and Robbins approach prefers arms, so if there's a larger theta. And both are optimism-based approaches. What is the connection between them? Okay. And so here it is. So UCB is a primal formulation. I want to maximize the upper confidence bound subject to the confidence interval. Okay, so this is UCB. Think of it as a primal formulation. And think of RBMLE as a Lagrangian formulation. I want to maximize, instead of putting alpha t up here, so this is the likelihood ratio, log likelihood ratio, and then I have alpha t multiplying the log of the optimal reward. I just divide it down. And think of this as a Lagrange multiplier, okay, for this reward, for this constraint. So what's happening is that the Lagrange multiplier chosen by RBMLE is actually 1 over alpha t. We hard code that Lagrange multiplier, okay? Whereas UCB will choose whatever is optimal for the dual, okay? But the fact that this does much better than UCB, in fact most policies do, suggests that so let's to look at this, right? Let's look at how close RBMLE is to the centroid of the confidence ellipsoid. Okay, because UCB will operate on the boundary of the confidence ellipsoid, right? Now, if our policy always is slack on that constraint, so it will be in the interior of that ellipsoid. How close is it? So this is here we're plotting just the distance to the centroid. So this is UCB on the boundary, and this is ours. But distance is not the right measure because there is a weighted quadratic, right? So write down, look at the weighted quadratic and write it, and this is still lower. So what this suggests is that maybe UCB is perhaps a bit too optimistic, hurting performance significantly, okay? Because it is way out on the boundary of the confidence ellipsoid. You come in much more, you will do better, and RBMLE seems to do well. It's much more delicate and in its optimism. Okay, by the way, we've also started re-examining the self-tuning regulator and started looking at finite time bounds, etc., and ultimately we can even show finite time bounds for self-tuning regulator. Okay, so not much in the way of concluding remarks. There's lots of adaptation algorithms that were studied in this period in control, okay, and one of the big distinguishing features of the machine learning or RL era is people are much more stringent in their performance evaluation. You look at regret, not just long-term average reward. And not only that, even if you have any pre-constants, you all ask how do those scale with the dimension of the system, etc. So much more stringent analysis, okay. There's lots of scope for examining many of these things. And this policy seems to have good theoretical regret performance, empirical regret, pretty low computation, at least in the case of Bandits. But for other problems, it's much more. And that's all. Okay, thank you.
We have time for some questions.
Yeah, so it seemed to me.
You want the mic?
No, I'm loud now. Yeah.
It's live.
Okay. So it seemed to me that your RBMLE policy depended a lot on knowing what the optimal strategy or the optimal value is for each theta, because it's part of the way in which you choose the estimate. Whereas things like UCB and so on might not be so dependent on that. That's my sense anyway. So is there some way to replace something that V opt theta by something empirical in modify your RBMLE policies that doesn't depend on the model so much? That's the question.
Okay, no, that's a very good question. Let me make different levels of comments. The first is any monotone function is fine. Okay, so right away there, if there is some known monotone function of it, that's good enough. Okay. Second thing I want to say is that is this a model-based approach as opposed to a model-free approach? So I haven't talked about it here, but recently we've even looked at kind of a linear parameterization. We've looked at other parameterizations which are more in the direction of model-free. Actually, the calculating upper confidence bound even for UCB requires knowledge.
It could be, yeah.
Yeah.
I mean, it can be treated empirically, but often it would involve the model.
Yeah, so we are trying to, I think there's a lot of scope here for completely empiricizing even that part, just like the likelihood part. Can you, I think there's,
Yeah, great talk. So following up on Venkat's question, so what's really nice about the approach is you have this spot which says, okay, let me calculate what the value of the policy would be had I known this was a true system, and you use that to bias towards estimates in that direction. What if that reward model is wrong? So the actual reward model is something, but it uses a simpler proxy for that. Is there a sense of, to get the right estimate, you have to have the exactly right reward model, or can a coarse approximation also give you these advantages? Kind of robustness with respect to the reward model.
Okay, so reward actually comes in two places in our thing, but it always comes up in at least one place in any other approach also. Basically, after you have some idea of what the system is, whatever, you need to choose an action. At that point, you should know something about the reward structure to choose the action, right? In our case, it also comes in because we are adding this term which favors parameters with larger average rewards. Yeah. I mean, if instead of that we know some monotone proxies or something, I suppose that also would work. And by the way, I used that trick in the bandit problem to get the indices. Okay.
Yes, so I'm intrigued about how this relates to, let's say, new approaches that are a bit blind. And you try something, you see the reward that you get. So you are learning the reward function as you go along. So it's completely model-free. Can one say anything about that? Maybe if the system is in a particular class, one could prove something.
Yeah, I mean, I have not. I think this is so we can try to empirically estimate the reward function as we go along and try to prove some theorems. I think that'll have to be done in any case. If you don't know the reward, you'll have to kind of estimate it anyway. So maybe you get some reward plus a random value or something like that each time, right?
Yes, so there may be a question of identifiability of the reward function, right?
I think much more difficult problems would be what they call sparse reward, like chess. I know whether I'm winning or losing only after 50 moves. I don't get a running reward. So then how do you do that? Yeah, I don't know.
Are there any further questions for Kumar? No? Okay, so let's thank Kumar again.